In section 14.3, we're going to be taking a look at partial derivatives. I'm going to start with a function of two variables. So z is a function of x and y. All of this will generalize to when we have w is a function of x, y, and z. Okay. Now, if I think about what a derivative generally means, graphically I'm thinking of it as the slope of a tangent line. That seems a little bit difficult here, simply because the graph of this is going to be a surface, not a curve. And if I have a tangent line, that's going to be tangent to a curve, not to a surface. But I also think of a derivative as being a rate of change. What's the rate of change of my output with respect to my input? Now here, my input is a point in 2 space. So the question we're basically asking is, if I vary my location in 2 space, how does that change the output? How does that change the z value, or the height of this function? That's ultimately what we're going to be asking. But because our input is multidimensional, if our input is a point in 2 space, it has 2 parts to it. And so what I can do is I can look at that rate of change one part at a time. And that's what we're doing when we look at partial derivatives. So I could say, what if I just changed x? How does coming forward or back from a point affect the z value if I'm not moving left or right? So hold y constant but let x vary. Or I could say, what if I don't move forward or back, but I just move left or right? How does changing the y value change the output of my function? So just looking at how each individual input variable affects the output variable is what we're doing when we take a look at partial derivatives. Okay, so let's suppose I have a point P naught with coordinates x naught, y naught. Okay. If I wanted to take the partial derivative of f with respect to x at this point. Okay. Couple of ways I can denote that. One way is just to put a little subscript of x. So if you put the name of the function followed by a subscript, that subscript tells you that's my variable. So that tells me everything else I'm going to be holding constant. Okay. All right, and I'm looking right now at evaluating it at a particular point at P naught. Okay. I could also write this as the partial derivative of f with respect to x at x naught, y naught. Okay. Or the partial derivative of z with respect to x at x naught, y naught. Doesn't matter whether I call it the name of the function or the name of the output variable. But notice, this looks kind of like our d by dx notation, but instead of being a d, it's a del. Okay. It's this sort of curved thing that indicates that we're talking about a partial derivative rather than a full derivative. Okay. And what this is going to be is I'm saying, okay, I want x to be my variable, so I'm holding y constant. So I can basically create this new function, f of x, y naught. That's now a function of just one variable because I'm holding my y value constant. And so we will say that if we take the full derivative of f of x, y naught, this function of one variable, and I evaluate that when x is equal to x naught, that's what the partial derivative at this point is. So I hold y constant before I take the derivative. Then I take the derivative of that. I've created a function of one variable, and then after I take that derivative, I would evaluate it at that point. Let's take a look at a particular example, and we'll be able to see what this means graphically. So let's go with z equals f of xy equals x squared plus y squared. So that's my lovely paraboloid. And let's say I wanted to calculate the partial of f with respect to x at the point 1, 2. Okay. Okay, so that says I want x to be my variable, so I'm going to be holding y constant, and I'm going to be holding it constant at 2. So geometrically what's happening is I'm looking in the plane y equals 2. Now that plane is parallel to the xz plane. I'm basically taking this and I'm slicing it with the plane y equals 2 and looking at the cross-sectional curve that I would get there. Okay. So if I look at the function f of x2, that would just be x squared plus 2 squared, or x squared plus 4. So the cross-sectional curve that I get in that plane is just this parabola right here with its vertex where x is 0 and z is 4. And of course we're concerned about this point right here. Notice in the plane y equals 2, that's the point 1, 4. When I plug in 1 for x, 1, 5. When I plug in 1 for x, I get out 5 for z. That would correspond to, over here, the point I get at 1, 2, 5. Here I don't need to label the 2 because I'm in the plane, y equals 2. Okay, excellent. So what we're trying to do now is see what's the rate of change of z with respect to x. So I'm saying this is the full derivative of this function, x squared plus 4. That's my f of x2. That's the function of one variable I created by holding my y value constant at 2, and I just need to evaluate that when x is equal to 1. Okay. All right, well, I can do that. That's going to just be 2x evaluated at 1, and so that's going to be 2. Notice, that's the slope of this tangent line. So the partial derivative is the rate of change of z with respect to x if y is held constant. And that's equivalent to the slope of the line that's tangent to that cross-sectional curve, or that trace that we get of this surface in the plane y equals 2. Okay, excellent. So there's our first example of a partial derivative. Now we were evaluating it here at this point. So you'll notice that what I did is I created this function of one variable by plugging in 2 for y. But let's suppose I wanted to look at the partial derivative of f with respect to x in a different plane, at a different y value. Okay. Well, then I'd have to create a different function here. What I did in this case is I plugged in that constant value for y first, and then I took the derivative. But if I want to, what I can do is I can say if I wanted to take the partial with respect to x of x squared plus y squared. Now here, this is a partial derivative operator. When there's nothing written on top, whatever comes after it is the thing that you're taking the derivative of. Same convention as with the d by dx's. If I were to write something on top, I would not want to do del f del x, x squared plus y squared, because that is complete in itself. This would mean the partial derivative with respect to x multiplied by this function. That is not what I want. But if I don't have anything on top, then this fills in that role. This is the thing I'm taking the partial of. Okay. Now, if I do that, and let's say I wanted to evaluate this at the point 1, 2. Okay. I could say, okay, so I'm treating x as my variable. That means I'm holding y constant. So the derivative of x squared is just 2x. If y is constant, so is y squared. Okay. So the derivative of that is going to be 0. So I'm treating it as a constant, but without specifying which constant it is. And then when I go to evaluate that at 1, 2, if there were any y's in my formula. In this case, it turns out they've completely dropped out, but now I would be plugging in 1 for x and 2 for y, and so I would still get 2. Generally speaking, that's what we will do, rather than plug in for one variable, the variable that we're holding constant first. What we'll do is we'll just say we're holding that constant. So I'm going to treat it like a constant, but without specifying ahead of time what it is. And that way we can get to a formula for the partial derivative, which we can then evaluate at any point. So essentially that frees us up to say, okay, I don't have to do this one plane at a time. I don't have to look at the plane y equals 2, and then look at the plane y equals 3, and then look at the plane y equals 4. I can just say, here's the formula for the partial derivative with respect to x that I would get in any plane parallel to the xz plane. And then you can plug in the appropriate y value for your point after you've calculated that formula.